Hey, thanks for joining again. So last time we talked about adaptive radix trees in general, the classic vision of what an adaptive radix tree data structure is. So in this video, I want to go over how I implemented an adaptive radix tree. I did it in JavaScript, and I didn't do it exactly the same way. It's not a perfectly faithful implementation of what is discussed in the original Adaptive Radix Tree article, ARTful Indexing for Main Memory Databases. So I want to talk about the pros and cons and how I did them differently now. Also, that means we're going to talk about the use cases of my tree, and I just want to lay that out there. I'm not saying that this is the way that you should do it if you want to create one, and I'm not saying that this is the best way to do it. This was a big project for me, and I learned a lot doing it. And that means that realistically, if I had to go back and do it again, I wouldn't do it exactly the same way. Okay, so I'm going to be a little explicit about that and tell you the things that I maybe wouldn't do the same. Okay, so the first thing we're going to talk about is, we talked about these one-way paths, okay, and how when you have these one-way paths in your tree, in between your nodes, your larger nodes like node 4, node 16, etc. These one-way paths, right, where it's only one character in each, well, if you implement these nodes with node 4, that can be wasteful. And so we talked about how in the original article he gave this idea of prefix vector. Okay, so vector, by vector, of course, I just mean a vector data structure, which is just an array, right? An array, and it can grow indefinitely when you add stuff. That's how vectors work, right? If you run out of space, then the data structure, what it does, it'll just conjure up a new array, twice the same as the last one, copy everything over, and it just keeps going that way. Every time it runs out of space, it'll double. So you can use a vector like that as kind of a supporting data structure in your larger node types to have these one-way paths. Now that can get a little bit complicated, okay? We talked about that last time. So I went a different direction. I'm going to explain the direction that I went in and why you might do it. Now I'm not going to lie, what I ended up doing, it works, and it was a really interesting experiment. But I am going to say that I can't say that I would for sure do that again, okay? And so here's what I did. So just forget about this for now. Okay, so you have a node 4 here, and say you have like a node 16 here, and you have this one-way path in between. Well, what I did, okay, so one-way path, I mean, just to recall, each of these is like a single character, okay, A, F, a 9, okay. So what I did was I implemented, instead of a vector, I implemented a linked list, okay. And what's a linked list? Well, you have links, okay. So in my case, they work like this. Okay, so you have a character here, so for example, 2, an A, right? Maybe I should have done the same ones as over here, but whatever, just arbitrary characters, a Z. So that's how I did them in JavaScript, is just an array of length 2. The character that you have goes here, and for the code point, actually, we have numbers, and we'll talk about that, but then in the second index comes a pointer or a reference, right, to the next. I'm just going to do that with an arrow to the next, to its child. Okay, so this saves a lot of memory compared to a node 4. It's a lot easier to reason about too when you think about the things that we have to do with the tree. Now, before we talk about the advantages of it in terms of ease of implementation and what you can do, I'm going to give you the downside first. Okay, the bad news. This uses a lot more memory. than a vector, especially in a language like JavaScript. And why is that? Well, we got to do some fancy footwork. So first of all, we don't have, you know, some type of, we have to use an array like this where each of these, realistically, each of the entries in this array is actually like a reference or a pointer, which you can guess it's probably going to take like 8 bytes a piece. Okay, and then there's probably some metadata that the engine needs to store for the whole array. And then you got to figure out what you're going to put here, and so you want to make it as small as possible. Well, I know that I need to put store 1 byte of information there. Okay, one of 256 possible values. But you can't just use a JavaScript number, right? Because that's going to be 8 bytes. And so my decision was, I'll take that, the code point for whatever the letter or character is, say 212, and I'll use a JavaScript function to convert that number to a string. Okay, so I'll do like, it's called string from char code, and you pass in this number, and it'll give you the character. Okay, and then I put that, and the character is only, you know, JavaScript strings are UTF-16, which means there's 2 bytes per character or so. And so then I just put that string there. And then if I want to read what code point it actually is, I decode it to that number. Okay, so that's how I do it, not that important. And then this is just a reference to the child node. So this uses a lot more memory, okay, than a vector. Because a vector is just, there's some metadata, but each index is just, you know, it's just 1 byte. Okay, so this can use actually a profound amount of extra memory. Now, I shouldn't say profound, because profound would be if you just were completely lazy and used node force. Okay, so I do it that way. What's the advantage of doing it that way? Well, all kind of things you can do with your radix tree, a lot easier. Okay, that much easier actually in retrospect. In retrospect, I might have, if I had to do this again in the future, I might actually just use a vector. But what kind of things can you do that are easier with these one-way paths? Oh, you want to be really careful. So, what kind of things? What can you? Oopsies. Can I wipe that off? You can. Oh, that's cool. So, what kind of things can you do that's easier? Well, when you're inserting things in the tree. Okay, so let's say you're inserting things and you've reached a node 4. Now you've reached a suffix of the key that you're inserting after this that's not shared by anything else. Okay, and so it's a one-way path that leads to a leaf. Well, it's pretty easy to create these things. Okay, so that's one thing. If you're removing things, okay, you can just, you know, I mean, they're very easy to work with. Range queries. Okay, this is a big thing with tree data structures, okay? Because if you don't need to, what is a range query? Well, it's like you have a bunch of different keys stored in your tree. This isn't just radix trees, this is any tree. Well, you want to go over, you want to iterate over them in order, right? So hash-based data structures notoriously difficult to do that because the way hashing works, it picks a random spot in an array for your keys, and so trying to get them out in a particular order is very difficult. Radix trees and other trees like binary search trees, trees in general, there's some tax that you're paying usually with a tree, but the benefit is they make it very easy to range over the keys, okay? So you can do things like, you know, iterate over all the keys in the tree in order from lowest to highest or highest to lowest. You can also give a lower bound and an upper bound. So let's say that you had the numbers 1, 2, 3, okay, all the way to 9,999. Okay, these are the keys that you have in your tree, and you want to iterate over a bounded range of them, which means you give a lower bound and an upper bound. What would the lower bound be? Well, let's say 954, and maybe the upper bound of 975. Okay. Trees make it very easy to provide those bounds, and very quickly, without having to search through the whole array, they can just enumerate just the keys in that range. Okay, that's kind of a bigger picture reason that you would use a tree. And in my view, if you want to do those kinds of range queries, and you don't have to do this with numbers. Let's discuss another example. Let's say you have a bunch of strings in your tree. Okay, so let's say we have a name Dave, John, and a bunch of other names, okay? And you want maybe all different lengths. These are both 4-letter names, but you can have all different length ones, okay? Variable length keys. Then you want to give a range of them. You can give a lower bound and an upper bound too, right? A lower bound string and an upper bound string. I didn't implement a function like this, but in theory it's possible. You could give a lower bound and an upper bound. All right? Strings that are less than or greater than a particular bounds. You can also do prefix searches. Those I implemented a lot of functions for. And what does that mean? Well, tell me all the names that start with DA. Okay? And then it'll tell you very quickly. Well, we have Dave. Maybe we have Dan. Okay? Maybe we have Dane. Alright? So, very quickly, tree data structures are great for that. And, in fact, radix trees, a type of trie, right? Tries are also known as prefix trees, so they're supposed to excel at these types of queries. Again, all these types of things, a lot easier to reason about when you're dealing with linked lists rather than these prefix vectors attached to your nodes. So that's one reason that I did it that way. Okay. Now I'm not going to lie. Realistically, I didn't give these linked list nodes the same. I call them node 1, by the way. I didn't give them the same full set of functions. Okay, exact set of methods with the same names that I gave to all the other node types. And so what does that mean? Well, I ended up having to treat them differently in my code anyways. And at the end of the project, I realized, well, if I have to treat them specially anyways, I have to treat these vectors specially too. So, and it uses more memory, so I'm not going to lie. But if you're like, I just want a working trie data structure, there's no reason that you can't do this. Just because in the original Adaptive Radix Tree article, they talk about doing it with vectors, you don't have to do it that way. It's not against the law to use a linked list. In fact, there's a history to doing it this way too. I was reading a little bit by Donald Knuth, famous computer scientist, and back in the day he made a reference to another paper by a gentleman named René de la Briandes, I think. I don't know how to pronounce his name correctly, and I actually looked up that paper and I read it, and they were talking about effectively a trie type of data structure that used a sort of a linked list pattern. Okay, so this is kind of an older idea, and it's a way to get your trie off the ground if you're maybe kind of struggling with this vector idea. Okay, so let's talk about also, so that's one thing that I did. Now the other thing that I want to talk about is how we solve some decision making with the larger node types, okay? So let's say we have 256 entries in this array and 48. Okay, so I'm not very good at drawing, but and 48 in this one, okay? This is the layout, if you'll remember from the last video, for a node 48. Okay? So if you need your memory jog on how that one works, go back and watch that video. But with this one, you have your key byte that you're inserting, and let's say it's 116. And so what do? Well, you find the 116th index. Okay, that's where it goes. Without a doubt, that's easy. Okay, 116. Now, which of these slots do you put its child? The reference to its child or the pointer to its child. Okay, this is an allocation problem, and this is something that I did one way that's not discussed in the literature, to my knowledge. And I'm not recommending that you do this. So this was an experimental decision, and I think it was interesting. But I will be honest, I don't know if I would do it again. Okay, I'm not as doubtful as I am about that with this decision that I made, but I am going to say that, well, I would benchmark other options for sure. Because the fact of the matter is, in JavaScript, it may seem foolish to do a linear search through an array, for example, for the first empty slot. But you know what? Languages like JavaScript have a little bit of magic up their sleeve. And the benchmarks to this project taught me that it can be extremely difficult, or impossible even in many situations, to beat the speed of iterating native JavaScript data structures like arrays and sets. Okay? Because they have lower level engine optimizations and implementations that do that. Extremely difficult to beat that. So I would for sure benchmark that in the future if I did another project like this. Now I ended up going in a different direction. How do you decide? Well, I decided to use a bitmap. Okay, so the bitmap makes it easy because the bitmap data structure, that's another subordinate data structure. But the bitmap, you can ask it, okay, what's the first unset index? Okay, and it'll look in the bitmap at the first, the index of the first unflipped bit, and it will tell you which one, and then you can set that one in your bitmap, and poof, there you go. Okay. Same problem actually with there are similar speed concerns with node 256. Okay, where you have just the 256. So you have 256 indexes in here, right? But when you are deleting key bytes out of here and you get down to 48, well, what do you have to do? You have to shrink this node 256 to a node 48. Okay, and again, like I said, iterating arrays in JavaScript extremely fast, but it still to me felt like, well, or in other cases, by the way, not, do one thing at a time. So copy values from here to your new node 48. Well, you're going to be, if you're just searching, you're going to be, iterating over a bunch of empty indexes, mostly empty indexes, to find all the things that actually have something, and that feels a little bit stupid. Now, actually, it might not be. And it might be worth it to benchmark it, but the way that I decided was, well, I'm going to bitmap it. And there are other benefits too. So in these cases, I'm discussing the allocation problem, right? How do you find the first set or unset indexes, okay? But there's another problem, and that's, I spoke about these range queries, ranging over. That may be a primary use case for your whole tree. I mean, dead serious, with this type of data structure, that may be the primary use case. And if you want to range over a bounded range of keys, that means in these types, okay, you're going to want to range over a bounded range of key bytes. Okay, so you may have a bunch of random key bytes and values in here, but you only want to iterate over a bounded range of them. So that'd be difficult to do without just doing linear searches, but with a bitmap, that's possible, because bitmaps make it very easy for you to iterate over bounded ranges of the bits, of the set bits in your bitmap. So that was my decision. I use bitmaps to manage these indices, and it worked out well for me. It's very quick to find the first thing. It uses a little bit extra memory, and you feel a little bit less stupid. Now, granted, in the grand scheme of things, that might have been actually a complete waste of time because, as I said, iterating arrays, as I found out later, it's very fast. So that would be worth it to consider benchmarking. But I just want to lay that out, that that's an option that I figured out, and I didn't really see it in the literature. So, okay. And how would you implement a bitmap in JavaScript? Just a little side quest here. Well, there's this function, this math function, okay? It's called like close32, okay? CLZ32. And what it stands for is count leading zeros, okay? So when you're doing, you have a JavaScript number which is 8-byte double kind of thing, but you want to do bitwise arithmetic on it, okay, in order to do some, bit mapping. Well, you can, when you do the bitwise stuff, it treats it as a 32-bit number, and count leading zero function, what it does is it counts the leading number of zeros in the binary representation of your number. So you have 0, 1, 0, 0, whatever, yada, 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 all the way to your 32. It'll tell you how many, it just counts the number of leading zeros. So in this case, it would be like 2, okay? Unless it does it from the other, I don't know. That's a technical detail that you have to figure out and work out like I did. But, that's the key to implementing a bitmap in a language like JavaScript, because count leading zeros, that'll tell you the index of the first set bit, okay? Or unset bit, because you can flip all these bits very easily too, right? If you're like invert all of these, and you can get one that's like this, okay? All right? So same thing, you can go back and forth, you can do whatever you want. And then what you can do too is if you're iterating, if you want to iterate all the set bits, Well, then you can go like this. Okay, so you start with this, count leading zeros 2. Okay, so then you do whatever you need to do with this one. You take a copy of this number, and you set that bit. Okay, so then you're left with this. Okay, and the copy of your thing. Now you count leading zeros again, and that'll take you to this index. Okay, then turn that one into 0, and count leading zeros again, and so on and so forth. And so that way you can very neatly iterate over all of the set indices in your bitmap. And so you can very easily iterate over the things, the 48, the sparsely used indices in your node 48. Or the node 256. And so this is how I did it. And a little bit of monkeying around to get the subordinate data structure working. But, it worked out great because it's very easy for these range queries, right? So that's the, I keep on dropping my pins. So that is the major things that I did differently. So let's talk about something else here. So we have our tree, and we want to insert keys into it, okay? Now, as it turns out, not all keys, actually by default in JavaScript and in many languages, these things where you want to put in the tree, numbers and strings, they're not binary comparable, okay? What that means is, or the order that you come up with, if you sort the keys by comparing them byte after byte, okay? So if you have a list of keys, strings or numbers, whatever, and you start with the first byte in all of them, and then you sort all of them based on those values, and then as a tiebreaker you go to the second byte in all of them, and then you sort all of them based on so on and so forth. That's kind of what you're doing with this kind of a data structure. And if you do that, well, one of the problems that you're going to run into is that you're going to come up with a different order than you are probably expecting. Okay, so if you do it with JavaScript numbers, which are these floating point double things, you're going to come up with a different ordering than the ordering of the numbers from a lower to higher magnitude. You just are. Because as it turns out, these floating point numbers like doubles, they're like their own little miniature file format, so a special thing is required. So what that means is you have to transform these numbers into a binary comparable format. And so he gives kind of a little bit of a riddle in the original paper on how to do that, and it took me some while to figure it out. And I in the write-up for this, I gave some, how I figured out how to do it. Basically, you end up computing a rank, and then I make that as the, I put that rank value in the 9. So what does it mean by a rank? Well, you have like 0, 1, 2, 3, 4, 5. And you compare which each of these is like a category. I think it goes all the way to 9. Each of these are a different category, like negative, not a number, negative infinity. Okay, and then like negative normal or something like that. I think that's it. Negative denormal. And then we have like negative 0. Then we have like positive 0. And then so on. And the opposite side is just this way, but in ascending order. It's positive, not a number. And so you just calculate which of these categories it falls into. Okay, and then this rank number that corresponds to that category, that becomes the first byte in the binary comparable version of your key. And then the rest of it, you got to put them in there and then flip the bits a little bit, because some transformations in order to make them binary comparable. So I don't want to get into too much detail. I did it pretty much, I think, the way that it seems like he describes that you're supposed to do it. And the tests passed, actually. The numbers seem to be ordered correctly. I'm just going to mention the thing about it is doing this in JavaScript, it seems a little difficult, because you have to calculate in this floating point version of the number in order to figure out which of these categories. Oh, you got to, floating point numbers have this thing called like a mantissa, and then there's like the exponent or whatever, and you got to separate in the sign bit, and you got to compare each of these separately. And how do you do that in JavaScript where everything is one of these doubles? So I actually implemented it in AssemblyScript, which is this compile to WebAssembly language. And it worked out great. It's a lot simpler to reason because they have the features that you need to do things like that. And you get a little WebAssembly thing. And then you send your JavaScript number into the WebAssembly module, and the WebAssembly module just returns this integer, and then you're good to go. So that's how I did that. And then strings. Strings are also not binary comparable. Now, why are strings not binary comparable? That seems like, well, actually they are, but the ordering that you come up with when you sort them the way that I was describing, right, where you compare the first byte and all of them, and then the second byte, and so on. Well, the order that you're going to come up with is in terms of the ordering of their code points, like in an ASCII table, for example. And you're like, well, why wouldn't I want to do that? Well, the reason that you wouldn't want to do that is because the order of those code points is such that the entire lowercase alphabet, I don't actually remember the order. I think that either the entire uppercase alphabet is before the entire lowercase alphabet, or vice versa, and that's a problem, you know, because it means that lowercase a and uppercase a, for example, aren't going to be, those strings, you know, aren't going to be sorted near each other, right? So actually, this gets to a bigger problem. So this relates to culture or localization. So like different people in different parts of the world, even if they use the same alphabet, they have different expectations about how different strings or text is sorted in different situations. And so because of this, what you need to solve this problem is something called a collation. And so collation helps you solve this problem. It's an order that's specific to that cultural or locale need for how to sort of things. So like, you know, there might be a different there might be different sorting orders slightly for strings in you know, the UK versus the United States or whatever. And also the other reason for this is that collation allows you to have tiers, okay, for sorting, right? So sometimes you want every character that's different to be different. So that means that in the letter E, whether it has a little or an N, you know, whether it's uppercase or lowercase, or it has a little accent character over it or not, doesn't matter. All those different versions of that character, they're considered separate. But in other situations, you don't want that. In other situations, you don't care about casing, right? You want different cases of the same character. Lowercase f and uppercase f to be considered the same. So collation allows you to do this. And I did a lot of reading about this, and there's this thing called the Unicode collation algorithm. It's really intense, and I realized I didn't need all of that. So I thought, you know what, I want to create, but a lot of people, I think the sentiment is that you couldn't really do this in JavaScript, or you wouldn't. Well, I did. I created a collation, but I did a simpler one. I did what's called a Latin1 collation. So it's all the characters that fit in the range of 0 to 256, or sorry, 0 to 255. And so there's actually, this is another data structure called Latin1, and you can put your JavaScript string in there. Now it's a lossy conversion, okay? Because if you have out of range code points, you know, beyond that 255, then you specify a character that you want to be replaced with. Okay, so in theory you could lose data, but you just have to be smart about it, because you do have an alphabet of 255 characters to work with, and so you can be, if you're smart about it, it can work for you in a lot of situations. And so I implemented this, and how did I do it? Well, I didn't come up with it myself. Actually, it's surprising JavaScript doesn't have like a native collator that you can use to produce these binary comparable versions of your strings for like a different locale. But they do have functions in JavaScript, collator functions that allow you to compare different strings. Okay, so you can give it a certain locale and two strings, and it'll be like, okay, let's see which one of these is greater or less than the other, and so then you can use that function to sort a list of strings. So that's how I actually came up with the Latin1 collation that I had. I pulled a list of all of the different locales supported that would be reasonably interested in the Latin1 range of characters, and then for each of those, I went and I basically ripped off the ordering that was present in the collator by writing a function that would compare a bunch of strings that were just all of the individual characters from 0 to 255. and I did that for each of the tiers, right, for each of the locales. And so that's what that data structure is. It's a Latin1 collation. So you can put a string in there and tell it what level of sort key you want, whether or not you want accents to compare different or casing and whatever, and then it'll give you the binary comparable key. And that way you can store strings in your tree. Okay, so that's what I did. That's not necessarily different. That's what you're supposed to do, is use a collation. It's just that in JavaScript, there's not a lot of collation capability offered natively, right? So I ripped it off, and I gave the script that I used to compile it in the write-up for this, so you can check it out, and you can also use it for different things. But you can use it to put strings in the tree. So moving on here, we're going to finish up the last few topics related to this radix tree. And so the last thing is benchmarks, okay? The second to last thing is benchmarks. So that's where I tested a lot of these features, like the prefix searching, or just simple inserting. How fast can you insert a bunch of different keys, okay? And so I did a bunch of different ones until I basically got bored. And here's my conclusion, okay? And there's more benchmark data in the repo for this if you want to explore more, but whoa, that's a little close for comfort, isn't it? Let's try that again. So the first thing, and I got this from some YouTube video that I watched once, okay? Oopsies. Oh, glitching out here. So take all of the words in the novel Moby Dick, okay? So this means first you have to either find a list of all of the words in Moby Dick, not to be duplicated, but all of them, or you need to write a program to split the novel into individual words, okay, like an array or a list of individual words starting from, the beginning to the end. So that's what I did. I wrote one regex pattern that it's not perfectly accurate, but you can read up on different approaches for tokenizing words and novels and things like that. I just wrote a single regex pattern to do it, but you can get actually pretty in deep with the theory of how to do this. But in the end, to validate that mine was correct, I just compared how many words that I come up with compared to the more canonical counts that are out there for unique words, and I was pretty close. I was pretty close, not within even 1% or anything, but I think I was pretty close. So that was the first thing, and that wasn't too difficult. So then what you do, I dropped my thing here. Oh, that's interesting. I am actually taller in this game than I am in real life. Interesting. So then you iterate through that list of words, all 200-some thousand or whatever it is, word long in that novel. Each one you use the Latin1 collation to produce a sort key, and then you insert that into the radix tree. Okay? And what you do is then at the end it's a the tree deduplicates all of those words. Okay? So that you have a unique list. And so I did this with my radix tree, I did this with my binary search tree, and I also did this with the native JavaScript set data structure. So it's kind of an apples to oranges comparison with these data structures because they all have different strengths and weaknesses. Okay, they each have capabilities that the others do not have. But the long story short is the radix tree beat both of the other options. The radix tree can even deduplicate all of these words faster than the native JavaScript set data structure. Okay, uses a lot of memory, but really, I even could do it on my phone quite easily in Termux, and that was the most impressive benchmark that I had, that it even beats the native JavaScript set data structure. Because as later benchmarks showed me, the native JavaScript set data structure is very tough to beat. So the native JavaScript set data structure has some tricks up its sleeve through lower level engine implementations. For example, iterating elements in the tree. Okay, so ranging over all of them. Now, JavaScript set, it doesn't give you the keys in sorted order, but if you're just iterating them and you don't care about the order, you'll never beat the set data structure. it's ludicrous. It's ludicrous speed. So with that in mind, it makes it even more impressive that we're able to deduplicate these words. Now, this is also a testament to the bias that a radix tree is intended to take advantage of. Radix tree, what can make radix trees fast for working with your keys is biases in the data set, right? So if there are lots of shared prefixes, like there are in natural language words, for example, from novels, well, that's exactly what prefix trees are good at. Prefix compression, right? So that's what they're good at. And, hashing-based data structures, or even the binary search tree, that's a different kind of, they have different strengths, and so they're difficult to get there. I did some other benchmarks though. So I also inserted a bunch of UUIDs into the tree and also numbers. So those are examples of high cardinality data sets. They don't have a lot of shared prefixes, okay? And you're just not going to beat sets and binary search trees for the most part with a radix tree and data sets like those. You're probably not going to, especially not one that's implemented the way I did it, but you're just not going to, because the high cardinality aspect of it means that it's just difficult speed-wise. And also, even with the Moby Dick thing, it's fast, but it uses more memory than the other options. So, and this also reminds me, I just want to talk a little bit about trees and I want to talk about trees and binary search trees. One thing you can do with these, okay, you can do compound key indexing with these. So that means you can create compound keys. This is something that I did that was pretty important. Oh, look, my hand fell. That's weird. I only have one thing left. So let's say compound key. Like let's envision that you have a table. Okay, imagine like in SQL, right? You have a table with columns. Okay, so here's column 1, or just imagine like an Excel spreadsheet, right? And each of these columns has a name. Okay, and in SQL you can declare an index across multiple columns, right? So you want the indexes so that you can retrieve tuples or rows from the table by giving bounded ranges or restrictions for each of the columns that are in the index. Okay, so let's say this has 4 columns, but only these 3 are indexed in this kind of compound index. And the order matters, right? Because maybe you want, even though this is column A, this is column B, and this is column C, maybe actually you want to retrieve things in the order by giving the keys to be ordered in terms of column B and then C and then A. Okay, so you would declare an index with that order. Okay, an index on column B, C, and A. And there's different syntaxes and ways of doing that in languages, different SQL versions, and but this concept of a compound key, you can do that with this. And actually, I have functions to support that. And so, what can you do? Well, you can make compound keys out of sequences of numbers or strings. Okay, so you could make a binary comparable version of a number, which is a fixed length key. Okay, of 4 or 8 bytes or whatever, and you could have a variable length key concatenated onto the end of that. Okay, terminated by a null byte, which is what my Latin1 encoding does. And then maybe you have another fixed length key of 2 bytes or something, right? And so you can insert binary comparable keys like that, compound keys. And so why would you, where am I going with that? Well, if you think about it, you're like, Moby Dick, that's interesting. What if actually I didn't want to deduplicate them, right? I want to insert all of the words into the tree, but I want to also be able to have like the number or the index, from the original ordering of the word from all of the, so like the word Moby is in there probably a bunch of times, right? But you want to be able to, when you, for example, for a search interface, if you want someone to be able to submit the search term Moby, and then you pull up a list of places in the novel where it occurs, right? So you would want like an index for each of those occurrences. And how would you do that? Well, you make a compound key, right? Where the first part of the compound key is the word, and then the second
part after that is fixed length key, which represents the index. Okay, and then this index of which occurrence of Moby, that's like a tiebreaker, right? So Moby is in there, and then you have a bunch of tails off of it for each index. And then you can do like a prefix search for Moby, and then you can iterate over all of the different indexes, okay? So you can do that kind of stuff with a radix tree. You can also do that with a binary search tree, but you can do that with my radix tree because I give, a function for doing bounded ranges, for doing prefix searches, bounded ranges of fixed length keys, and that was a big reason that I did the linked list, was to make functions like that easier to reason about, because I found with prefix vectors, I'm like, I just want to get to the compound key indexing part, right? I want to be able to implement these kind of SQL style indexes in my programs. And in doing this, I also learned how to do it with binary search trees. And actually, in a lot of cases, even with prefix searching, it can be faster with a lot of data sets with a binary search tree compared to a prefix tree like this. So, anyways, we covered a lot of ground. These are the major things that I did differently with my radix tree. There's one more thing that we're going to talk about with my radix tree that I did differently. And what is that? Well, can I do it over here? Can we write on this? No, we can't write on this, can we? No. Okay, we'll just write it over here then. You know what? It's fine. Let's put this down and we'll just erase this. So, you can also use a radix tree, especially one like mine, that has these linked lists for the one-way paths that make them easier to use. You can use them to compile massive regex patterns. Okay. Oh, by the way, before we get to that, I did another test similar to. Sorry, I'm so excited about this topic because I worked on this for so long. I'm so excited to share. I also did a similar test like Moby Dick, but I did it with the complete works of Shakespeare, and again, the radix tree was faster. So, anyways, back to what I was going to say. This is the last thing. So you can compile regex patterns, okay, using a trie. You can compile a style of regex pattern or regular expression called a trie regex pattern, or as I like to call it, a trie style regex pattern, because it's not truly a trie. A trie has a data structure like this, but I happen to have a job where I write a lot of regex patterns, and a big concept with regex patterns is alternation, or providing different options. So let's say that you need to write a regular expression that can match any of these. Okay, the name Dave, the name Dale, the name Dana, and then maybe we'll do also the word deft, okay? So you need to write a regex pattern that can match any of those strings, okay? So a common way that beginners will do is they will just concatenate these like this. We'll just have Dave, and then there's this alternation operator, a pipe character, okay, so Dave, Dale, okay, and another pipe, Dana, and then, you know what, we're going to skip this one actually. So, that's called a trie regex pattern, and that's not a trie regex pattern. Sorry, that's kind of a naive way of doing this. This is a simple example, so it doesn't really matter with something this small. But even then, it can. Okay, efficiency is a concern because there's usually a performance tax for using regex patterns, and due to the way that they're implemented, and they can. The thing is, regex patterns are often scheduled to run many times. Okay, so your regex pattern could be scheduled to run over massive data sets many times, and so small things like this, small inefficiencies matter. So eventually you'll realize that you can use grouping constructs to make this a little bit more efficient. These have a shared prefix of DA, right? So another way to write this is you can just match the D and the A, and then you can have a group, okay? A group of alternatives, okay? So VE, pipe, LE, pipe NA. And that's called a trie-style regex pattern. Again, this is a small example, but there are times where you need to have many alternatives. Okay, and so you realize it's more efficient to do this, right? Because this way you match D, A, V, and then you could have a situation where, oh no, the next letter is not an E. Oh, now we got to go back. Okay, and then we got to start over again, even with the. And so this you can cause backtracking if it's a backtracking regex engine, or if it's an automata simulation style one, it's maybe some non-determinism with the automata that you pay a little bit of a performance tax with, and so you realize eventually all these options. There's a DA, so just match it right away, and then you can focus on choosing between these different ones. And you can do this with, as I said, you can make really big regex patterns following this. You can nest these groups and nest them, and so that's called a trie-style regex pattern. All right, and you can, like I said, there could be a shared prefix in here with more groups and so on and so forth. And so when you start to do this, and you start to do this kind of a thing when you're writing them, because even at a computer it can be a little bit challenging. So you start to get a notepad open and you're like, okay, let's use some indentation here. And you start to be like, okay, so VE, and then pipe, LE, and so writing kind of like in a nested, giving yourself white space to keep track of it easier, and it gets real convoluted. And you know what? I've written these by hand, and they take a little bit of time to do, and sometimes you're up against a time crunch, and it's not possible to do that fast by hand, even if you're a really fast typer. Okay. Sometimes the nature of the situation, you have to get these a bunch of these real fast, and so you can compile these, okay, using a radix tree. This is something you're not going to be doing with a JavaScript set, most likely, and you're probably not going to be doing it either with a binary search tree. See, with the Adaptive Radix Tree, you can do that, and I have a function to do that. And actually, I tested it. Okay, this function, I did it on that Moby Dick data set. I made a regex pattern that matches every single word in Moby Dick. Okay, so I inserted all the words from Moby Dick into the radix tree, and I used that function to compile a massive regular expression. That regex pattern in a file takes 116 kilobytes or so. So it's a massive pattern, but it compiles, and it will match every word in Moby Dick. So this thing really works. You have to use a Latin1 encoding or an encoding library of your choice, but I'm going to explain just briefly how it works. So it's actually real simple. So when you have these node 4, node 16, 48, these higher order types, okay, that store multiple of these. So you start at the root and you do what's called a depth first traversal of the tree. Okay, so you descend before you go across. When you're descending, if the node that you're at is one of these higher order types, okay, 4, 16, 48, 256, well, what does that mean? That means that that's the start of a group, okay? And as you're descending, if you encounter a node 1, well, that means that you're like concatenating onto a string that was the previous, so like each of these at the beginning of each option will be a key byte from one of these, from the node, the higher order node type that you're on. But then if the child is like a node 1, well then you're going to concatenate and just keep concatenating. Okay, so node 1 means concatenation, and then when you run into a higher order node type, then you're creating these nested groups, and that's how it works. It's as simple as that. It's just a depth first traversal where you're making that decision. The only other trick that I should tell you is that, well, you might support strings in your tree like I do that are prefixes of each other by using null bytes to terminate them. So you might be able to store the word Dale and Dales, okay, both of those words, Dale and Dales plural, in the tree, because each of these will have a null byte on the end of it. Okay. Now, what that means is you need to be able to be careful with that. So what I do in order to make sure that doesn't mess up the regex pattern is if I'm iterating one of these, and you're using stacks to do a depth first traversal, okay? As you're doing that, and you encounter one of these node types, and as you're iterating, you encounter that sentinel byte value, in my case null byte, but you can use other sentinel byte values. When you encounter a sentinel byte as a key byte value in one of those types, that means that that group is optional. Okay? And that's basically how I support both of those in the regex pattern. So you can support Dale and also the other, So that's what I do, and with the regex patterns, if there's more interest, I'll create another video on the details of how you can do this. But it's a really useful function that can make a lot of difference for you, even if you don't have massive data sets. Sometimes people talk about the performance of a radix tree in terms of it being beneficial only with asymptotically large data sets. Something like this. Excuse me. Something like this. A regex pattern compiler. This will save you a lot of time personally writing regex patterns, even with smaller data sets. Okay. So thank you for joining me. This is probably the last video that I'll make unless people have an interest in other things with my tree data structure. But I just wanted to give a review of my experience writing an adaptive radix tree. I was maybe foolish to do it in JavaScript, and I made some weird decisions, but it was experimental. And I'll be honest, in the grand scheme of things, I think a better Swiss Army knife tool that you would use in a lot of situations is probably a binary search tree. But this definitely has its use cases. So anyways, thank you so much for joining me, and have a good one. Bye for now.